Okay, so good evening, everyone. So welcome to lecture 38 of the course on data structure and algorithm. Uh, sorry, lecture 37. So in today's lecture, we shall be discussing about different types of trees like 2-3 tree, B plus tree, okay, and um, and another topic which is binary tree reconstruction. Okay, so let's come to B plus tree first. So I have shared my screen. So can you see my screen?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. So all of you please also open your in your device this corresponding note. Okay, the note is given there. Okay, so B plus tree is an advancement over B tree. Okay, so in B tree, a node contains key values based on which uh, okay. Oh, let me stop this B plus tree. I have to first uh, explain B tree. Okay, binary tree. Okay, okay. This is fine. Binary tree reconstruction. So in this topic, binary tree reconstruction. So see what is the uh, question here. See, we know that there are three type of traversal mechanisms in a binary tree. Those are in-order traversal, pre-order traversal, and post-order traversal. Okay, but this traversal mechanism or traversal technique of two different binary trees may have same sequence of nodes. So you are taking two different binary trees, tree 1, tree 2, and applying in-order traversal on both of them. You may have same result. Okay, you may have same result. So this code which I have shared with you, the BST code, this one, uh, yes. So you have seen the code, right? Binary search tree. So in its output, if I run the program, let's say insert one, enter the value to be inserted in the binary tree, binary search tree. So let's say give some value 11. Okay. Then let's say other insertion, let's say 8. Another insertion, let's say 15. Then insertion, let's say 5. Insertion 20, and so on. Okay. Insertion 8, 10. Insertion let's say 15 or 14. 14, right? Yeah, wait a second. 1, 11, then 1, 8 left subtree, then adding in the right subtree, adding left to 8, that is 5, adding right to 8, that is 10, adding left to 15, that is 14, adding right to 15, that is 20. So it's a complete binary tree we have constructed. So the root node is 11, left subtree is 8, having two children, 5 and 10, and then right subtree is 15, having left child 14, right child 20. So this is the complete binary tree. Now if I do in order traverse, so I'm seeing that 5, 8, 10, 11, 14, 15, 20. That's fine. In order traversal is resulting correct. Correct answer. Okay. But in this program, uh, if you just only show the datas 5, 8, 10, 11, 14, 15, 20, the answer is correct. But I am not satisfied. Why? Because it's an in-order traversal. Now, if I told you, if I tell you, so please construct the tree. I mean, why I will tell you that please construct the tree. So you are displaying in the output, uh, especially twixt group, B1 group. You have shown your outputs only the sequence of numbers 5, 8, 10, 11, 14, 15, 20. So your answer is correct. Then I told you, okay, your answer is correct. Okay, you can leave. Your marks is given. You have done good, very good. But still, I was not satisfied. Why? So because the statement problem statement which was given to you, you write a C program to implement binary search tree with a given sequence of number. So I am giving you given with a given sequence of not numbers, given sequence of operations. So what you are doing? Insert 11, insert 8, insert 15, insert 5, then 10, then 14, then 20. So if I give you a sequence of numbers for insertion, that will matter. That will lead to a unique construction of a binary search tree. Because if you shuffle these numbers, the tree construction may be different, something else, and its in-order traversal will be something else. So that means the forward statement is, if it is given the forward statement like this, key construct a binary search tree given a sequence of numbers, then you may have unique binary search trees. What I told you, let me write here. Forward statement, that is given a sequence of numbers or data, one can construct a unique BST. So that means if I am given a BST, it's the corresponding sequence of number. It may be in order sequence of number or pre-order or post-order. So the sequence of number will be also unique. So that is the converse statement or inverse statement. Okay. Converse statement. If I say that given a BST, it's in order sequence of numbers. Okay. Is unique. Okay. But this is false. This is not true. So this is very important observation. The forward statement is true, but the converse statement is not true. And to address this statement, to verify the statement, okay, we have a different problem today. That is the topic binary tree reconstruction. Okay, and then I mean. Then okay. Now coming to this point, this code. So this code is, I like this code because this code is actually making us to visualize the actual construction of the binary search tree. Okay, why? Because here I am actually showing a triplet of a node. Okay, so this is the first field is actually the address of the left child. This is the address of the right child. Similarly, the other nodes. So if I can visualize this display, then I can construct a binary search tree, and therefore I can verify that whatever the binary search tree I was supposed to construct, that has been actually constructed or not through this programming, that I can verify. That's why here displaying the nodes in this manner becomes very important, very crucial for validating that yes, the program is correct. Because if you show just the in-order traversal with the numbers, Okay, the numbers are coming, that's fine. Sorted numbers, some sort of sorted numbers. But whether the BST is constructed properly or not, all the links are connected, whether or not, how can you verify by this? That's why I always suggest to show the proper addresses, okay, which can give us more and more information, detailed information about the data structure. Anyway, so from this idea, so this topic is becomes important. If we are given an in-order or pre-order or post-order traversal, okay, of two different binary trees, they may lead to a same sequence of numbers. So reconstruction of binary tree is not possible from a single in-order, pre-order or post-order traversal. So what is the remedy? We can reconstruct a binary search tree or binary tree from if minimum two, or if an in-order traversal and a pre-order traversal information is given, then I can construct uniquely a binary tree. So to address this issue, an example has been taken. The reference of this topic is again Yashwant Kanitkar, data structure with C. A very good problem. Suppose an in-order traversal is given like this, and a pre-order traversal is also given. Now I know that using only this in-order I can't construct a binary tree which is unique, or given only pre-order I can't reconstruct a binary tree uniquely. Using the information of both in-order and pre-order, I can only construct the tree, reconstruct the tree. Okay. So in-order, pre-order are given. Now what is the logic? Very easy problem. First value of pre-order must be the root node. What is in order? Who want to say? Okay, answer the way. What is in order?
So left, root or right.
Yes. So left, then root or data, then right. And pre-order?
Root left then right.
Yes, root, then left, then right. So root, left and right. That means the first value must be the root node. Okay. From the pre-order traversal, you are having that information. The root node should be the first value. That is 1. So you write immediately the node 1, and it may have some left subtree and it may have some right subtree. And in the left subtree, what will be the numbers? All the numbers. It's a binary tree, right? Okay, sorry, it's a binary tree, not a binary search tree. Okay, so please be careful. This is not a binary search tree reconstruction. It's a binary tree reconstruction. So in the left subtree there will be some numbers, and in the right subtree there will be some numbers except 1. Okay. So right. Okay. So so now now you look upon the in-order traversal. Okay. Now what is the in-order concept? The in-order concept is here. Right? Something like this. So here is the left subtree and here is the right subtree. So if you are not done with the left subtree, you can't come back to this root node. What is the in-order traversal? Left, then data of the root node, then right subtree, LDR. So you must complete visiting all the nodes in the left subtree. Then you come to the root node and display the data, and then you go to the right subtree. That is the logic of in order, right? And what is the in order here? Information given 47285 have been displayed. Then 1 has been displayed, or 1 is present. What that means? That means whatever numbers are present to the left of 1, those numbers must belong to the left subtree. Yes or no? If it is 1,
Yes, sir.
all the numbers in the left subtree should be visited first, then the root node value will be visited, displaying 1, then all the values in the right subtree will be visited. Okay, so in the in order traversal, if you are given the in order traversal, so first 4 is displayed, and then 7 is displayed, then 2, then 8, then 5, and then 1. That means these numbers must have been visited earlierly and displayed earlierly as compared to the 1. That means these numbers must belong to the left subtree with respect to the 1. And similarly, these numbers which are present to the right of 1 must belong to the right subtree. So this is very logical. Okay, now all of you convinced about this fact, this
Yes, sir.
understanding?
Understood.
Yes,
Yes.
sir.
So immediately from that understanding, okay, we can sketch the left subtree and the right subtree. In the left subtree, what are the numbers? 47285. So those are mentioned 47285 in the in order. I can't construct fully as of now the left and right subtree, but yes, I can have this information. In the left subtree, the in order will be based on these numbers 47285. So don't shuffle these numbers. This sequence is very important, right? So in that same sequence, maintaining the sequence of the numbers 47285 will be the in order traversal left in the left subtree. And similarly, 693 in this order will be the in order traversal in the right subtree. Okay, so this is fine. Okay. Now, similarly, we want to come to the point for the pre-order traversal. So, anyone want to try the similar logic? Which portion of the pre-order traversal will be belonging to the left subtree and which one should be belonging to the right subtree?
So 2 to 8.
First, again, recall the pre-order concept. So, what is the pre-order concept?
Root left, right.
So, first you must display the root, and then you cover all the numbers in the left subtree, and then you cover all the numbers in the right subtree. So, now look upon this pre-order traversal sequence. Now, who want to try?
So 2 will be the root.
Yes.
Sir, 1 will be
1 will be a root.
One, huh?
So 2
1
will be the root of the.
একজন বলো।
So 1 এর left subtree 2 থাকবে ফার্স্টে।
Okay, next.
তারপরে 2 এর left subtree 4 7 থাকবে।
না না, আমরা
Right 8.
এই মুহূর্তে আমি বলছি লেফট সাবট্রিতে প্রি অর্ডারের পোরশন কয়টুকু থাকবে আর রাইট সাবট্রিতে প্রি অর্ডারের
স্যার
পোরশন
2 থেকে 8 স্যার 2 to 8 স্যার 2 থেকে 8 এটাই বলছি
বুঝছো?
স্যার উপরে ইন অর্ডারে স্যার রাইট সাবট্রিতে 3টে এলিমেন্ট ছিল 3 6 আর 9 তো প্রি অর্ডারে সেমই থাকবে তো স্যার ফার্স্ট হচ্ছে 1টা হচ্ছে স্যার রুট নোড বাকিগুলো যে এলিমেন্ট গুলো পড়ে থাকছে ওটা লেফট সাবট্রিতে
Yes. So one thing you have got an idea from the in order. What are the numbers in the left subtree? That is 47285. So based on 47285, the portion which contains 47285 must be in the pre-order. But maintaining the sequence of the pre-order, that means 24758. So these numbers, 5 numbers, are actually the numbers belonging to the left subtree, which you can see from the in order. And in the in order, what the numbers are present? 396. Now, tell me one thing. Is it possible that there exists another number which is not present in order but present in pre-order? Is it possible?
স্যার এটা তো নট পসিবল, কেন কি মানে
Yeah,
একটাই তো মানে
so it's an obvious case. That is the first thing we must be. It must be hitting in our mind. We have got a set of numbers. That is 47285. Those numbers will be in a sequence, in a different sequence in case of in order, in some other sequence in case of pre-order, in some other sequence in case of post-order. But the numbers will be those 5 numbers only. So it is not possible that one number is absent in order but is present in pre-order. It's not possible, because in order, pre-order, whatever order traversal you are doing, in order, pre-order, post-order, all of them are covering all the numbers. So in the right subtree you have this information. There are only 3 nodes in the right subtree. That is 3, 6. The 3 nodes of which values are 6, 9, 3. And what will be their positions? That we are actually gradually establishing from the information of in order and pre-order. So you got the point that left subtree contains 5 nodes, right subtree contains 3 nodes. Okay. So now again, whatever we have done for 1, we will be repeating the thing from this. So given in order 47285 and pre-order 24758. Who want to tell me which one will be the root node?
So 2.
Yes.
yes sir 2
So how to detect that? Very simple logic.
Pre-order
first
first
element.
So pre-order first element are 2.
If you want to find out the root node, the logic is very single line logic. Look, what is the first value of the pre-order? What is the first value of pre-order? 2. That will be the root node. Immediately, see, we have constructed 2. Similarly here, what is the root node of this right subtree?
3.
3
3.
Exactly. Immediately we are drawing 3. And then remaining portions we will be writing. So with respect to 2, we may have left subtree, right subtree. With respect to 3, we may have left subtree, right subtree. Now tell me one by one, if the root node is 2 here, what will be the left subtree? I mean, what is the set of numbers belonging to the left subtree?
4 and 7.
Correct. Why? How to detect that in single line?
So in order left এর 2
ওই
left.
দুটোই আছে, 12 লেফটে।
The set of
So in
numbers
order,
which are lying or which are present to the left of 2 in order. The answer is 4 and 7. So 4 and 7 in order sequence will be 4 and 7 are the numbers in the left subtree. What are the numbers to the right of 2 in order? 8 and 5. So 8, 5, those are the 2 nodes available in the right subtree of 2. Similarly, in 3, who want to tell me the set of numbers belonging to the left subtree of 3?
6 9
6 and 9.
6, 9. What will the set of numbers belonging to the right subtree of 3?
No
Empty.
number.
0
Empty.
Not 0. 0 is not here.
empty yes sir
Empty.
empty
Now, so see, we have immediately constructed. It's a very beautiful problem. Okay, and then from this again you can construct এটা দেখিয়ে দিলাম। এবার বলো, এটা দেখিয়ে দিলাম। হ্যাঁ, এবার বলো এখান থেকে কি করে করবে? In order 47, pre-order 47, তাহলে রুট নোট কি আছে?
4 sir.
4
লেফট সাবট্রিতে কি থাকবে?
so null
Null.
Yes. Right সাবট্রিতে
7
7.
good. So 2, 4 left child is empty, right is 7. Similarly, অন্য কেউ বলো এখানে রুট নোট কি হবে এই জায়গাটায়?
5 sir.
5.
5. হ্যাঁ, and left subtree of 5?
8.
8 কি করে হলো? ও বাইনারি ট্রি তো, আমি বাইনারি সার্চ ট্রি বলি। হ্যাঁ, 8 correct, and right subtree is null. Similarly here, with respect to this, what will be the root node here?
6.
Left subtree of 6,
Null.
right subtree
9.
good.
9.
Now we can easily reconstruct the tree. See how easily we can reconstruct a tree given in order and pre-order traversal. Now this logic is very, very important logic. This logic can also be applied to a problem. If you are asked that, okay, reconstruct a binary tree, but given in order and post order traversal, can you do that? Similar
Yes,
logic
sir.
you can try over there, in order, post order. ঠিক আছে? Okay. So this is very important problem. Okay, very good problem. So you may try with another other examples, other different examples from internet. Anyway, so now talking about 2 3 tree.
স্যার বলছি পোস্ট অর্ডারের ক্ষেত্রে একদম রাইট মোস্ট এলিমেন্টটা তো রুট হবে।
Yes. ওটা তো এখানে ছিল। Okay. So 2 3 tree. Okay, 1 second. প্রবলেমটা বের করি। প্রবলেমটা কোথায় আছে? Okay. The problem is given like this: 20, 6 5, 24. This is 3 5. Okay, so here illustrate the insertion of node 2 into a 2 3 tree as given in the figure. So the values are like this is 20, here it is 6 and 5, and there it is 3 and 5, it is 9, this is 17. Okay, this is 23, this is 24, and here 27, 33. Okay, so this is the problem given. Okay, so please note down the problem, or I think it's also given in the WhatsApp. So just open the picture image, I mean screenshot of the problem, and have a look on that. Otherwise you can note down. Okay, now 2 3 trees. properties of, this is a special type of a, okay, 2, 3 trees. It's an advancement of evil tree. Okay, the properties of 2, 3 trees are like this. Number one, all non-leaf nodes in a 2, 3 tree must be two or three nodes. Okay, which themselves be 2, 3 trees. Okay. So any node, any non-leaf node can have more than, 2 children or more than 2 children, 2 children or 3 children. So it's a special type of a general tree. Okay? So binary tree is a special type of general tree. So in binary tree, a node can have at most 2 children. But in general tree, we can have a provision that a node can have more than 2 children. And this is a special type of tree where a node is restricted to have exactly 2 or exactly 3 children. That's why it is known as 2, 3 tree. So number 2, levels of all leaves, okay, must be equal. Number 3, if any node have 2 children, then the node contains only one data field. Okay, I will explain this. Okay, so as it's an AVL tree, I told you that the properties of, so it's an AVL tree. Okay, it's an AVL tree. So we can't call it call it an AVL tree or binary search tree. Okay, so it follows the same principle of binary search tree. This part we can say. What do you mean by that? The values or the data fields belong to a left subtree will be always less than the data field of its root. Okay, you can see from here. So as this is a 2, 3 tree, so this is the left subtree of the 2, 3 tree, and all the data fields or values are less than its root node. Okay, that is the principle which is being followed in BST AVL tree. So that principle is also followed here in 2, 3 tree. Okay.
Sir,
So
I
that,
got one key concept is
but I mean to say that in binary search tree is the first tree which we have studied, in which this policy is followed, that all the values present in the left subtree should be always less than the value of root, and all the values present in the right subtree may be greater than or equal to the value of root. That principle is also followed in AVL tree. That principle is also followed in case of 2, 3 tree. So if any node have 2 children, okay, so for example 20 have 2 children, left child, right child, but this root will have only single data field, that is 20 only. Okay, so next line what I am writing, that is the set of data in LST, that is left subtree, okay, will be less than that of root, okay, and similarly the set of data in RST, right subtree, will be more than or equal to that of root. Okay. So here less than policy, here greater than equal to policy. Okay. Normally less than and greater than. Okay. Usually. Anyway, so number 4. If any node, so I told you that a node may have, a node must have either 2 children or 3 children. Okay. If that node is a non-leaf node. Okay. And if that is a leaf node, then all the leaf nodes must be in the same level. So this is level 1, level 0, level 1, level 2. And leaf nodes are nodes which don't have any child. So we don't have to bother about their left and right subtree. So this is regarding this point number 3 is for the children. What will be the characteristics of the children? That means these are for non-leaf nodes. Okay. So next, so these are for those non-leaf nodes which have exactly 2 children. Now what about those non-leaf nodes which have exactly 3 children? Any node in this tree must have 2 children or 3 children if that is a non-leaf node. Okay, so this is the case for non-leaf nodes having exactly 2 children. Now about 3 children. If any node have 3 children, then its data field, then it contains contains 2 data fields. Okay, for example here this node does have 3 children, child 1, child 2, child 3. So that node should have 2 data fields. One is 6, another is 15. Now if there are 2 values, then what will be the policy to be followed in the child branches? So that is something like this. Here it is less than, here it is in between 6 and 15. Okay, that means greater than equal to 2 less than, and here it is greater than equal to, means less than 6, here greater than equal to 6 but less than 15, and this right branch is greater than equal to 15. Is it clear? বুঝা গেল
So the intermediate position, তাই তো মাঝখানেরটা?
Yes, this is less than 6, this is in between 6 and 15, and this is more than 15 or equal to 15. Okay, so these are the possibilities. If we want to compare a value, that means okay, let me draw here. So somewhere it is 6, somewhere it is 15, and you are supposed to you are having a value x. That x may lie in this range, to the left of 6 may lie in this range, in between 6 and 15. That x may lie after 15. So that is these are the 3 possibilities where x may lie in this number line. So okay, because you are given only 2 values, 6 and 15, and based on these 2 values you may have exactly 3 possible cases, and that's why this node can have exactly 3 children. Okay, বুঝা গেল? এবার ক্লিয়ার হয়েছে পুরো ব্যাপারটা?
এই নোডের লেফটটা ভ্যালুটা তাহলে ছোট হবে, একটা বড় হবে, তাই তো?
ক্লিয়ার করে বলো।
স্যার যেমন 6 আর 15 আছে, 27 33, মানে একটা ছোট একটা বড়।
হ্যাঁ, কোথায় 27 33? হ্যাঁ, এবারে ধরো এখান থেকে তুমি যদি আরো ব্রাঞ্চেস বের করতে, তাহলে দিস লেফট ব্রাঞ্চ শুড ফলো লেস দেন 27, this branch
27
should follow more than 27, মানে I mean greater than equal to 27 but less than 33, and this right branch should follow greater than equal to 33. Is it clear?
Yes sir.
Okay, okay, fine. So if any node have 3 children, then it contains 2 data fields. Let's say those are val1 and val2. Okay, so then left subtree or left child, left subtree, okay, left subtree must follow less than val1. Okay, middle subtree must follow greater than equal to val1 but less than val2. X, okay, and then number C, right subtree must follow X greater than equal to val2. Is it clear now? So this is the policy of 2-3-tree. These are the properties or policies of 2-3-tree. What is a 2-3-tree? So you have to cover all the 4 points. These are the most significant points or features of a 2-3-tree. And in the next class you will see, actually আমার আগে বি ট্রি এটা পড়ানোর কথা, কিন্তু আগে 2-3-টা বলে দিলাম, তার কারণ স্পেশাল কেস দিয়ে পড়ালে হয়তো সুবিধা হবে. So in the next class we will see that we will have generalization of 2-3-tree. What is that? So from this concept you have an idea something like this. If a tree does contain, we can generalize this thing, if this tree contains data fields d1, d2, okay, and dk, that means this node will have exactly k plus 1 number of children. Am I correct? If
Yes,
there are
sir.
k number of data fields in a node, then that node must have k plus 1 number of children, and all those children will follow principle like this. This is somewhat less than d1. Okay, let me write here less than d1, the left child. Then it is, let's say the number is x, so x is less than d1. Then it is x less than greater than equal to d1, but less than d2. Then x, this third branch, first branch, second branch, third branch is greater than equal to d2 but less than d3, and so on and so on. So ultimately, if we have in middle 2 values, 2 data fields, let's say di and di plus 1, we can have something like this. Then x will be greater than equal to di but less than di plus 1, and the rightmost branch x dot greater than equal to dk. So this is the policy, the generalization of 2-3-tree, and we will talk about it in the next class. Now coming back to the problem, okay, how can we insert a value which is questionটা কি ছিল, insert a, okay, here insert a 2. How can we insert a node 2 into a 2-3-tree given like this: 20, 6, 15, 24, 3, 5, 9, 17, 23, 27, 33, and we can understand that, okay, as a left child of this node, 2 will be inserted, right? And how can we illustrate that in an answer copy? So a demo is given. So 20, this is the tree given in the question. Search position of insertion. So after searching for the position of insertion, we came to know that the 3 5 node, which is highlighted, that node is the position where we can insert a node 2. Now it is given like this: lose addition of node 2. Okay, so lose addition of node 2 means, okay, lose addition of node 2 means we are adding 2 forcibly inside the node as a data field, and as a result, what happens? This is something looking like 2 3 5 forcibly. This is done forcibly, and which is known as a loose addition of node 2. This is called like this. So if I do this 2 3 5, now it is violating the principle of 2 3 T. Why?
স্যার দুটো
স্যার ফোর
ডেটা ফিল্ড তো দুটোর বেশি থাকতে পারবে না ডেটা ফিল্ড।
I'm not getting anyone. Anyone?
আর ফোর চাইল্ড হয়ে যাচ্ছে স্যার ওই জন্য।
Yes, exactly. So 3 data fields in a node is not allowed at all, because 3 data fields will allow, there will be 4 children of that node, but 2 3 tree, any non-leaf node may have exactly 2 children or 3 children, no 4 children. So 3 data fields in a node is not possible. So this is violating the principle of 2 3 tree. So how to deal with this? Strategy 1. First strategy is you select the node, I mean its root node, that is 615. Okay. Before that, you split 2 3 5 node into different nodes, into different data fields, that is 2 3 and 5. So that is not shown here. So 2 is splitted, you can see from the picture. 5 is also splitted, as you can see from the picture, and 3 was there in middle of, in between 2 and 2 and 5. That 3 has been absorbed into its parent node. That is the strategy. Okay, so if 3 comes inside its parent node, now see what is happening. So this node contains 3 data fields, 3 6 15, but its number of children is equal to 4. So somewhat this portion of the tree is good, because if a node does have 3 children, a 3 data field, it must contain 4 children, 3 data fields, so 4 children. So that is correct. But again, this is not done yet, because it's a 2 3 tree. So what happened then? Then second strategy is, so you bring 6 into its parent node, 3 and 15. Okay, so I'm just illustrating here. I will talk about what is the loose addition in more detail when I will talk about 2 3 tree and B tree. I have to teach B tree, and then about this strategy. So then 6 has been absorbed into its parent node, so that it becomes 620, and it is left with 3 and 15. Okay, 3 and 15. 3 and 15 আছে, হ্যাঁ, এখানে 5 কেন? Then what happened? Splitting of 3 and 15. So if we split 3 and 15, so one is 3, other is 5, and 2 children, 2 and 5, are given to its parent 3, and 9 and 17, these children are given to their parent 5. Okay, now it becomes a 2 3 tree. 2 data fields, 3 children. 1 data, 2 children. 1 data, 2 children. So this is a very good technique, strategy, double strategy based addition of a number 2. Okay, very popular in 2 3 tree. So it's a very standard.
15 হবে না? 15 তো?
না, এটা 15 হবে। এটা এখানে যে
হ্যাঁ হ্যাঁ
এটা
ঠিক
লেখা
আছে।
আছে না কি ঠিক বুঝতে পারছি না। এখানে গ্রে কালার করা হয়েছে বলে ব্যাকগ্রাউন্ডটা হয়তো বোঝা যাচ্ছে না। এটা 15। So this is an illustration. How to write, how to show in an answer copy within very short time this kind of a process. So we are illustrating a process of insertion of a node in a 2-3 tree, and if you can't actually insert like that, because how can you insert if you just insert as a left child of 3 and 5, but it is violating the principle, second principle. What is that property? That all the leaf nodes should be in the same level. So you can't actually directly add a node 2 as a left child of 3, 5. So that's why to tackle with this, we are following this kind of a procedure. But this procedure has been taken from a foreign university, so you can have a faith on this, no problem. Okay, so loose addition of node 2 possibly into that node of where you are successfully finding the position of insertion, and then a double strategy, strategy 1, strategy 2. And how to split, how can we actually split, what will be the algorithm, what will be the logic, we will discuss in more detail when we talk about B-tree. Okay. Okay.
আচ্ছা স্যার
Yes.
একটা জিনিস স্যার, আমরা যখন স্ট্র্যাটেজি 1 স্ট্র্যাটেজি 2 যখন অ্যাপ্লাই করছি তখন
Yes.
মানে ডেটা ফিল্ডস এর যেটা মিড যে ভ্যালুটা ওটাকে আমরা মানে তার প্যারেন্ট নোডে পাঠাচ্ছি, তাই তো?
Yes, yes, yes.
ওকে,
ঠিক আছে, এটা আমি এটা লিখিয়ে দেবো, রুলস এন্ড প্রপার এটা দেখিয়ে দেবো, মানে স্ট্র্যাটেজিটা আমি লিখিয়ে দেবো, স্ট্র্যাটেজি 1, স্ট্র্যাটেজি 2। ঠিক আছে, এটা লিখিয়ে দেবো।
ওকে স্যার।
তো ভালো লাগলো আজকে দুখানা প্রবলেম, 2, 3 ট্রি অ্যান্ড বাইনারি ট্রি রিকনস্ট্রাকশন, খুব ইজি প্রবলেম। খালি এখান থেকে প্রোগ্রামিং ইমপ্লিমেন্টেশন করতে হবে না, এগুলো জাস্ট লজিক্যালি কোশ্চেন আসে, লজিক লিখতে দেয়, ড্র করতে দেয়, খুব ইজি। আর এগুলো কোনো স্টুডেন্ট অ্যাকচুয়ালি অ্যাটেন্ড করে না, কেন পড়াশোনা করে না, লাস্টের দিকে থাকে বলে। কিন্তু এগুলো পড়ো, এগুলো খুব স্কোরিং জিনিস, আমি জাস্ট একটু বুঝে বুঝে করলেই হয়েছে। ওকে, সো 2, 3 ট্রি হয়ে গেল। বি প্লাস ট্রি, বি প্লাস ট্রিটা তো 10টা বেজে গেছে, তাহলে আজকে পারছি না, নেক্সট দিন করাচ্ছি। আমি ওটা নোটটা দিয়ে দিলাম, তোমরা একটু পড়ে রাখতে পারো নেক্সট দিন। তাহলে in the next lecture we will cover B plus tree and B tree and the strategy of insertion in case of 2, 3 tree. Okay. So any doubt, if you have any doubt, you can ask me, and if you have any anything to say regarding the marks of your CA2, then you can also ask me. And regarding the solution, if you have any doubt, you can also ask me. Solution টা এখানে আছে, সলিউশন তো মানে স্ট্রেট ফরওয়ার্ড, সবকিছু দেওয়া আছে এখানে আশা করি। নাও কেস অর্ডার অফ, এটা আমি প্রুফটা এখানে অ্যাটাচ করে নিয়ে আমি দিয়ে দেবো, এটা পুরনো সলিউশন। যেটা অর্ডার অফ এম, এটা হচ্ছে অর্ডার অফ এম প্লাস এন হবে, পলিনোমিয়াল অ্যাডিশন, মাল্টিপ্লিকেশন এম এন হবে। এগুলো দেওয়া আছে সিম্পল, এগুলো তো প্রসেস। আচ্ছা, এটা বোধহয় তোমাদেরকে আমি দিয়েছিলাম ক্লাস নোট আগের বারের সলিউশন থেকে, তোমরা কেউ ফলো করো না। এখানে অনেকেরই নাম্বার কাটা গেছে, তো কালকে হয়তো যখন ক্লাস টেস্টের কপিগুলো ওপেন হয়ে যাবে তখন দেখতে পাবে মুডুলে। সেটা হচ্ছে যে এখানে এই জিনিসটা মেনশন করতে হবে, ঠিক আছে, যে 6 এর পরে টু অ্যাড কিউ rear has to rear must be incremented to 1. Always whenever you are trying to insert a new value, rear must be incremented by 1, so it becomes 7, and 7 is not possible. So there, this is very crucial. Keep whenever rear is equal to 6 has reached the last index, you are actually reinitializing that rear to 1 and you are doing insertion, but you are not mentioning whether front is not equal to 1 or not, because if front is equal to 1, so you can't insert, that is full. So that condition you must satisfy and must mention in the answer. So rear has to reinitialize with rear equal to 1, Okay, in the first index of the circular queue, provided front not equal to 1. Because front equal to 1 and rear equal to 6, this combination signifies that the circular queue is in overflow condition. Okay, it's the so it is not in the overflow, there is a vacancy, so you are placing the queue in the position of index equal to 1. Okay, এটা তো লিনিয়ার সার্চ ছিল, চারটা তো কেউ করনি, চারটা সব থেকে সোজা কোশ্চেন জানি না কেন করনি। লিনিয়ার সার্চ অ্যালগরিদম, এইখানে আমি সবাইকে 5 দিয়েছি, 6 দিইনি, বিকজ many of you have written the algorithm here, ঠিক আছে, but just 1 mark deducted if you have used a variable name tr or something fast or something tame. What are those? At least write a comment, those are missing. That's why this is important. Linked list node definition is important. Here we came to know about what is the meaning of data, what is the meaning of p, which we are using in the algorithm. Whatever you are using in the algorithm, you must specify the variable, the significance of the variable, the usage of the purpose of using a particular variable mentioned in the algorithm. ঠিক আছে? Whatever variables you are mentioning in the algorithm, make them specified. What is their role? What is their purpose? Okay. Okay. আচ্ছা, বাইনারি সার্চ অ্যালগরিদমের কমপ্লেক্সিটি ডেরিভেশনটা অনেকেই বিএসটি দিয়ে করেছো, বাইনারি সার্চ ট্রি দিয়ে, ওটা করলে হবে না, বিকজ বাইনারি সার্চ ট্রি আমরা তো এই মুহূর্তে পড়াশোনা করানো হয়নি, তাহলে ওটা তুমি কি করে করলে? আর যদিও বা একজন দুজন করেছো অ্যালগরিদম কনসেপ্ট থেকে, জানি না কিভাবে করলে, কিন্তু সেখানেও কিছু কিছু মানে পুরোপুরি ঠিক নেই, তাও ওখানে পার্শিয়াল মার্কস দেওয়া হয়েছে, 6 ওখানে 2 বা এরকম টাইপের কাউকে দেওয়া হয়েছে, ঠিক আছে, যারা ওই অ্যালগরিদম কনসেপ্ট থেকে করেছো, রিকার্সিভ ফাংশন ডেফিনেশন থেকে করেছো, তাদেরকে ওই কারণ এখানে ইনকমপ্লিট আছে, সবকিছু মেনশন করেনি, তাই আদারওয়াইজ ঠিক আছে। ওকে, so let's stop the class here. Let me take the attendance. Somartho,
প্রেজেন্ট স্যার। স্যার লিভ করবো?